All right, boys and girls, welcome back to the drive-thru. Sponsored as always by the deli. Hungry? Stop by the deli. Get yourself a Black Forest ham and Swiss with sweet hot mustard on some flaxseed bread, toasted, and if you don't mind, let's put some sweet gherkin pickles on there and just flavor it up. All right, here we go. This is a two-dimensional, oh my gosh. There's a two-dimensional projectile problem that we're going to do in parametric form, okay? Remember that the general form for projectile motion is that, okay? Where VO is your initial velocity involved with both functions, okay? T is the amount of time that the ball was in the air, involved in both functions. And then H is the initial height, and G is gravity. H and G only affect the Y aspect of these functions. So first, I want to make sure you guys understand the setup of the problem. That's the path the ball has taken, okay? Remember that a vector-valued function produces vectors over periods of time. So when you put in a t with the initial velocity that we're going to find and a launch angle of 45 degrees, an initial height of 3, and gravity measured in 32 feet per second squared, that this is what the path will look like. And at some time t, you get this vector. Well, this dot represents the position of the ball at that time, but the vector itself is a position vector. It's made up of an x-coordinate, which would be determined by that, and a y-coordinate, which would be determined by that, okay? So you're going to need to understand, in general, how vector value functions work to understand this problem. You could do this problem if you know how to solve a system of equations, but there's doing the problem and then there's understanding the problem, and those are two totally different things as we're learning. So, as we plug in the given information, you'll get R of t. Cosine of 45 degrees is radical 2, well, 1 over radical 2. And I'm not even going to simplify that because I find it easier to just leave the radical on the bottom, as some math teachers out there are freaking out. And then this one becomes an initial height of 3 plus when you plug in 45 degrees, that simplifies to this, and then minus 16t squared. So when you plug in the given information of a launch angle of 45 degrees and an initial height of 3 feet, then you get this function. Okay. So, with the information that we have given to us, I know that at some t value, that this thing has traveled 300 feet in this direction. And at that same value of t, at that same time, excuse me, this should say 300, it didn't, right? At the same time, I know that our h will be 3, again, based on the given conditions. So I will also write 3 plus VOT over radical 2 minus 16t squared equals 3. And now what we have here is a pretty simple, well, I shouldn't say simple. It's a system of equations, two variables. If we solve this one for t, you get t equals 300 radical 2 over VO. Notice how leaving the radical 2 on the bottom actually made that easier to solve. Okay? So if I substitute that in for both values of t over here, I'm going to write this out because it gets quite complicated. You get 3 plus VO 300 radical 2 over VO radical 2. This radical 2 is there. This VO is here. 300 radical 2 over VO came in from there. Hopefully you can see that. Minus 16 times 300 radical 2 over VO squared equals 3. Okay? The 3's are gone. You end up getting, the VO's are gone, the 2's are gone. You get 300 equals, move that over, 16 times 300 radical 2 over VO squared. Squaring that out in your calculator gives you 300 equals 16, well, let me just write that out. Okay, you get 300 equals 2,880,000 over VO squared. Cross multiply and divide, and you get VO is about equal, let me scroll down a little bit. You get VO is about equal to 98.0 feet per second. Okay, so there we've solved it for our initial velocity. And let's scroll back up to the problem and always keep in mind what the heck we're being asked. What was the initial speed of the ball? 98 feet per second. Okay? How high does it rise if it is caught 3 feet above the ground? Well, there's a calculus way to do this, which I think is the best way, but you also can understand that just so happens that since this problem was hit at 3 feet and caught at 3 feet, that the highest point, the apex point, will be the symmetric point in between there, okay, which will happen at 150 comma something. So you could plug in 150 for your x value and solve it that way, but that wouldn't really always work. It would only work because of the symmetry of this problem. So let's think about this. When will the ball reach its highest point? It's going to reach its highest point when this function is maximized, because remember, this function represents the height of the ball at all points t. And when that thing gets maximized, when that green line is maximized, then we have hit our apex point. So we are going to need to optimize this equation when we go on to the next page. So we essentially have y equals 3 plus 98t. The 98 came from our VO over radical 2 minus 16t squared. So y prime is, okay, that's gone, 98 over radical 2 minus 32t. And we want to know where this tangent line will equal 0. Well, that's going to be at its maximum point. So now, since I've found the tangent line, I will set that equal to 0. and solve it. So you get 32t is 98 over radical 2. So t is 98 divided by radical 2 divided by 32, which is t equals 2.165 seconds. How high does it go? Okay, well, let's go back to our original equation right here, and let's just get it as an ordered pair because I want it to make sense. So at a VO of 98 and a T of 2.166, so 98 times 2.166 divided by radical 2, comma 3 plus 98 times 2.166 over radical 2. Let me move this. Minus 16 times 2.166 squared. That's going to be a vector. Let me pop that in the calculator. And you get 150, about 150, 78. And I hope that makes you feel good. I mean, that's great. We had a 300-foot hit, and at exactly halfway point, because it was hit and caught at 3 feet, you'll have it be about 78 feet tall. Now, where are we going? The next thing we're going to think about is, guess what? This ball did not travel 300 feet. It traveled significantly further than 300 feet. It traveled 300 feet in length, but how far did it actually travel? Well, that's what we got coming up. Boom!